So, what if you could solve two of the biggest mysteries in the entire universe? I'm talking dark matter and dark energy with just one single, really radical idea. Well, some theories are proposing exactly that, and they're pointing to something called defects in spacetime. I know, it sounds like something straight out of science fiction, right? But today, we're going to dig into a source that asks a really important question. Is this a brilliant solution, or is it all just cosmic nonsense?
Okay, so let's break this down. On one side, you've got the heavyweights, dark matter, that invisible glue holding entire galaxies together, and dark energy, the totally mysterious force that's making our universe expand faster and faster. And on the other side, you've got this proposed solution, these tiny little defects, or singularities, in the very fabric of space-time itself. The big idea is that these imperfections could actually explain all that missing mass and energy. It's a beautifully simple concept, isn't it?
But hang on a second. The source we're looking at today says, whoa, let's pump the brakes. It argues that before we get totally swept away by this really elegant theory, we might be skipping some pretty crucial steps. You know, are we even asking the right questions to begin with?
So here's the main point the source is making. Before we can even start talking about defects in spacetime, we have to have a rock-solid fundamental understanding of what spacetime itself is and what it can even do. It's kind of like trying to describe a crack in a wall when you have no idea what the wall is made of in the first place. So what are these really basic questions? Well, things like, what properties would spacetime even need to have to support a defect? And at what scale could something like this even happen? Are we talking about the subatomic, quantum level, or something else entirely? The core argument here is that without solid answers to these questions, the entire theory is just built on sand.
And from there, the critique gets even sharper. It moves from just the basic properties of spacetime to questioning the actual physical processes involved. I mean, this whole theory requires spacetime to behave in a very, very specific way. But does that line up with what we know about reality?
So the source poses this absolute killer of a question, and it starts like this. How does the fabric of spacetime, this fundamental construct of our entire universe, how does it even tear?
For a defect to actually become a singularity, I mean, just stop and think about that for a second. What physical mechanism, what force could possibly cause spacetime itself to rip? The theory just kind of assumes this can happen, but it offers absolutely no physical reason for it.
And believe it or not, the critique goes even deeper. Now it's targeting the very words, the language that the theory uses. Proponents throw around terms like singularity and infinitesimal all the time, but the source is asking, do these words even have any real physical meaning in this context?
Right, so we've all heard the definition of a singularity. It's a point of infinite density. But let's just pause on that. Infinity is a mathematical idea. It's a concept. What does an infinite amount of something packed into a single physical point actually look like? Does that even make sense in our universe?
And it's the same deal with the word infinitesimal, a quantity so incredibly small that it's basically zero. Again, it's a brilliant tool in math and calculus, but can you really apply that to the physical fabric of spacetime? The source flags this, using these mathematical ideas as if they're real physical objects, as a major flaw in the theory.
Now, to try and get around these tricky definitions, people who like the theory sometimes use analogies to explain it. But our source pretty much calls this hand-waving and points to one specific comparison that it says completely pulls the rug out from under the whole idea.
Okay, here's the direct quote. The theory compares these space-time defects to defects in atom rosters. Think of a crystal lattice, like in a diamond. On the surface, it's a pretty helpful analogy, right? You can easily picture a single atom missing from a perfect grid. But this simple comparison creates this huge hidden problem.
And this is just brilliant. This is where it all kind of falls apart. See, if you compare spacetime to a crystal grid, you're implying that spacetime isn't smooth and continuous. You're suggesting it's made up of tiny, individual units, or pixels. This idea, discrete spacetime, raises a whole new, massive set of problems and questions that the original theory wasn't even built to handle. So the very analogy they used to explain the theory ends up disqualifying it.
And this brings us to the source's final powerful verdict. It says, and I quote, that it's nonsense to suppose defects unless you really base them in a material description. So when you boil it all down, the crucial point is this. A beautiful idea or a helpful analogy, it just isn't enough. For a theory in physics to actually mean something, it has to be built on a real physical foundation, not just abstract concepts and fancy comparisons that totally fall apart when you look at them too closely.
And that really leaves us with a fascinating question to chew on, doesn't it? In this huge quest to solve the universe's greatest mysteries, what's better? A beautiful, elegant theory that's maybe built on nothing? Or just admitting that for now, we simply don't have a theory at all?